Okay, we can look at log and exponential functions, and we can look at what the transformations are. So for a function, when we have this exponential function, there are some restrictions. Okay, x can be, and we can try to understand these restrictions in terms of the shapes of the graph as well. So this is exponential graph. Okay, x can be all real values, no problem. There are restrictions on y. The f of x is going to be greater than 0. Okay, it can't be equal to 0. We also know that the base, okay, the base cannot be 0. Base not equal to, sorry, can't be 0 or negative. So the base must be greater than 0. Okay, can't be equal to 0. And we can't have the base equal to 1. Okay, 1 to any power is 1, which is not a function. The y values don't change in that case. So if there's our domain, or domain then, we'll write our domain more formally. Domain is from negative infinity to positive infinity, and the range is from 0 to infinity. Okay, we have restricted values for our base, so in this case here, a must be greater than 3 and a not equal to 4. Okay, we can write the x and y intercepts. There are no x-intercepts. The y-intercept of this function, okay, anything to the power of 0 is going to be 1. So in this case, the y-intercept, that part is equal to 1. So the y-intercept of the expression is equal to 20, because we're going to multiply that by 20. Find the inverse. Inverse means we switch the x and y. Okay, so the inverse, I'm going to take that same function, and I'm just going to switch the x and y. Now what's implied then is I want to solve for y. So I'm going to solve for y by putting into log form. Before I do that, I'm going to divide that 20. And now I'm going to convert it into log. Log base a minus 3, the base of the exponent, the base of log should be the same. The argument is going to be x over 20, and that's equal to y. Okay, so the domain and range of the inverse, well, the domain and range should just switch. So the domain is going to be from 0 to infinity. Okay, I can put numbers from that are bigger than 0 to infinity in there. I can't put negatives or 0 into that log. Okay, so that's my domain. My range is going to be infinite. So from negative infinity to infinity. Okay, so there's my domain and range. Okay, I think I forgot to put a bracket in here. Okay, so the domain and range, my x-intercept in this case, so it has a y-intercept of 20. My x-intercept is going to be equal to 20. So when y is 0, x is 20. So 20 divided by 20, the log of 1 is equal to 0. Okay, so that's my x-intercept. So all the values change. This one has no x-intercept. There is no y-intercept on this graph. If I were to sketch this graph, it will just be a log function that looks like that. Okay, and it crosses at 20 here, x-intercept at, y-intercept at 20 over here. Okay, looking at exponential growth. Okay, we have our basic exponential growth formula. It's going to look like this. The end amount is equal to the start amount times my growth factor. That's my multiplier. And to the power of growth cycles. Okay, so looking at this problem here, this is compounded monthly, 30% annual interest. So how would I write that? That's going to look like this. So I start with $100. I'm calculating an end amount in this problem. Okay, so we're starting with 100. What's the appreciation? So we're trying to calculate the end. And we're going to do compounded monthly first. So this is part A. So this is monthly. my growth factor, if it's 30% a year, each month I have to do my growth factor for each month. So it's going to be the 30% divided up over 12 months. Okay, and then the number of compound cycles is going to be 12 because we have 1 year, and this is the power should represent the number of months. So this is my growth factor, monthly growth factor, so my power should represent the number of months or the growth cycles. So in this case it's going to be 12. Okay, so using a calculator, I need to punch that into a calculator. So punching that into my calculator, I'm going to end up with 100 bracket 1 plus 0.3 over 12 to the power 12. I'm going to get $134.40. I'm going to round that to 45 cents. So my appreciation for this 30% per year, well, I get an extra $4.45 for compounding it monthly instead of compounding it at the end of 1 year. Okay, so if I just compounded it once, I'd only get $30 on the 100 that I started with. Okay, so then let's look at this same problem, but we're going to do it daily. Okay, so daily. So what does a daily look like? Okay, same exponential growth problem, but now the 30%, we're going to figure out how much of that interest is used each day. So I'm going to divide that 30% into 365 increments, and then we're going to apply this interest, not once, but we're going to, over a year, we're going to apply this 365 times. Okay, so this is getting to be more and more compounded, and in fact, it is leaning now towards more continuous compounding of interest. Okay, so this if we've talked about this before, we may or may not have talked about this before, depending on which videos you've gone over. But a continuous growth cycle, a continuous growth rate, would be when this 365 would be infinite. Okay, and then we start using this E function instead of this compounded growth factor, or sorry, this compounded growth formula. Okay, we start using the E equation instead. But here we are compounding it daily. We can count the number of compounds, and when we calculate this, punching this into our calculator, again we're going to start with $100, 1 plus 30%. Now this time we're going to divide that 30% into 365 units, and then we're going to compound it 365 times, so we get $134 and looks like 97 cents. Okay, so we get a little bit more, so we get about 52 more cents if we compound it daily instead of every month.